Mexico right now, is what I'm saying. All right.
Just don't go anywhere in America south of Canada.
Pretty much. Pretty much. Yeah. 49th parallel. Stay there. You'll be okay. Right. So today we're talking about what, I don't know, I think this is the meat of the course now. As I said, we talked about analysis of variance. We're not going to talk about factorial ANOVA. This table wasn't like this. Anyway, factorial ANOVA, which is a little bit different. Again, you all know what this is, but it is going to be a way to solve a certain kind of problem. So here's some data I made up. Those of you in my memory class may recognize the idea of having different retention intervals, 5 minutes, 1 hour, and 24 hours, for remembering a list of words. That's what we have here. And the percentage, it's actually, those are pretty reasonable. Again, if you're taking a memory class, you'd know that those aren't bad numbers. Those are about what you get. So if I give you a list of, say, 20 words, you'd probably remember about 90% of them 5 minutes later. 1 hour later, about 70%. And 24 hours, about 60% probably. Okay? Once you hit a week, it's around 20%, 30%. So that's fine, you could do that. Now, again, you're not winning, this isn't anybody's honors thesis next year, I just give you a really cool idea. Ebbinghaus did this already, like 1890, so this isn't your thesis next year. But you may be using, hell, if you work with me, there's about a 50-50 chance you do something with a list of words. It's something I'm interested in. So you do in your ANOVA, you conclude that retention interval affects memory. No shit, Sherlock, boy, no big Nobel Prize for you. So, still, that's a perfectly solid experiment. It's the kind of thing we do a lot in lab courses, things like that. We know it's going to work, and we'll get a significant effect. So we can even play with the data a little bit. Fine. Here's some more data I made up. And these data are about levels of processing. There are three different levels of processing. Again, if you're in memory, you should know this because we have a test coming up on Friday. Low, medium, and high. A low level of processing is the surface features of a word. So how many ascending and descending letters are there? Like a D goes above and a P goes below. Medium level, count how many syllables there are. You have to say the word to yourself, but you have to think about what it means. You have to count how many syllables there are. I don't care if you're right or not. I'm just trying to see how deeply you're processing it. And finally, we could use a deep level of processing, which would be, on a scale of 1 to 7, rate the pleasantness of this word. Now you have to think about the meaning. And you get something like that. The higher the level of processing, the better something is remembered. It should also be noted that the better something is remembered means the higher it's processed, which means that it's an entirely circular concept. But anyway, it's circular. It was originally developed as a way to classify memory experiments, not as a theoretical framework. All right. Okay, so you do the ANOVA and you find it again. Levels of processing affects memory. No shit. Again, you're not winning a Nobel Prize for this one. But you'd find this and it would work, and it's very reliable effect. Craig and Lockhart, 1972, the paper this is based on, has been cited 18,000 times. Kind of a big deal. All right. So, thing is, what level of retention interval should I have done the level of processing experiment at? And what levels of processing should I have done the retention interval experiment? Good question. Thank you. I know it is. I thought of it. Now I'm literally just talking to myself. It's come to the point. That was like making up video lectures during the pandemic. That was like that. I'd be sitting there and I'd have all my stuff in front of me and I'd be talking, making little jokes. But I put laugh track in. Mine, me, so I did that. I'd go off. I still meandered off telling stories. It's the same thing. You didn't get the full Dave Brodnick experience because I didn't say a lot, but I figured it was recorded. But anyway, how do you do this? What do you do in this situation? Also, sometimes in those, out of nowhere, someone would just walk in the room I was recording in, and I would say, we've got a cameo. So I just treated it like I had my own show. So again, not that different from now. So what would we do? what to do, what about we do something like that? That's what we do, we combine the two designs, right? So we have different groups, that's what the G means, so group 1 up to group 9. Get used to the idea of G, whatever, it's a term, it's a sort of a notation I use. So what this is saying is we have different people, group 1, group 2, group 3, 4, 5, 6, 7, 8, 9, in each of these cells. So each group is a bunch of people, I don't know, 5 people, whatever the hell it is, on each group. So here we have a low level of processing and a 5-minute retention interval. And group, I don't know, let's go, group 6 has a medium level of processing and a 24-hour retention interval. Okay? And again, I know that you've read into Factorial ANOVA before. Let's really get into it now. Okay. So questions up to now, because this is sort of introductory, now we're going to get into the meat of this stuff. Okay. Or I don't know, if you're a vegetarian, we're going to get really into the tofu.
Yes.
That's fine. Or the seitan, or whatever weird thing you eat. It's fine. Tofu can be delicious. It's actually flavorless, but it can be delicious.
Lots of canned beans. So much canned beans.
Yeah. You do lots of stuff. Well, that was fun. I didn't expect that. Sometimes I made these slides up. You know, spoiler alert. I made these slides up 20 years ago because this shit doesnn't change, eh? So you can just keep it. But I forgot that I did that. Anyway, x equals mu plus alpha beta plus epsilon. I'm sorry, the alpha and the beta do not mean type 1 and type 2 error. I'm sorry. It's not my, I'm not no, forget it. I'm not going to apologize. Learn that there's a different alpha and a different beta, okay? So that's the effect of A. So first of all, any score, let's just deal with this what we normally do, is any score equals a grand mean, and again, that's the score we would all get if we weren't in any groups and there was no difference between any of us. The effect of variable A. So if we want to call variable A the one across the top, was that level of processing or I don't care what it was. We're going to call it variable A, just one of the variables. And then we got the effect of variable B, that's beta. Right? And we've got, this is the new part. Actually, the rest of this is the same as before, except now we get two variables, A and B, instead of just one called T for treatment, right? But fine. We've got this new thing called an A-B interaction. And of course, we still have error. So the new thing that we have here, the only way this has changed from what we've been doing so far, is that we have an A-B interaction. What that means, it's the effect of A and B together over and above the effects they have on their own. Right? So it's over and above the effects they have on their own. So, I don't know. Let's think of an example here. Women are on average paid less than men. This is not going to be a happy example. But it's a really good one. So women are on average paid less than men. They shouldn't be, but they are. I'm not supporting that in any way. I shouldn't have to say that, but some idiot will think I am. There's a reason I don't ever run for office, besides the fact that I don't want to do that. It's because there's so much of me talking on the internet that I'm unelectable. So being a woman's harder than being a man. You get paid less. It is. It's not right. It is. Being a person of color is harder than being a white person. It just is. You're playing on a harder level. Being a woman of color is harder than being either of those things, just those things put together. That's the extra part. Like I said, it's not a happy example, but I think it's one that we all understand. Right? Best part was the year I got into a little argument with a little incel talking about that. That was fun. What is it with people? They're all such idiots. Right. So that's all it is. It's just the effect of the two things together over and above the two things by themselves. hey, if you're in neuropharm, it's a super additive effect. It's literally what it is. So if you took neuropharm or you're in neuropharm and you've heard me talk about super additive effects of drugs, that's what that is. I mean, it's a mathematical expression of it. It's not really super additivity, but that's what the interaction is. Okay? All right. Questions? Okay, good. Very good, very nice. So let's get a little more deeply into this. So we don't just look at A and B. So in our example is what? Retention interval and levels of process. We're looking at how the two things act together, how they interact. It's like the whole is more than the sum of its parts. It's almost like the Gestalt kind of thing. Right? That's sort of what's going on here. So here is a definition of what it is, and if you can remember this, you'll be fine. And it's the effect of one variable changes depending upon the level of some second variable. Okay? It's funny, I teach it here a lot. I'm surprised the carpet isn't worn out. One day said if Arthur and I taught all the classes, there'd be no carpet left because we just move around so much. Right, questions on this? Does this make sense? If this is making sense, this is great. And I'm not surprised it is. You're smart people. And I'm really good at this. But if you have questions, ask them. Because this can be hard too. But if you're all following it, this is awesome. Okay, very nice. So here's, as I say here, a picture is worth 1,000 words. This is an interaction. So here we have, let's look at, I'll use this one here. So this is some variable, I don't know what they are. I don't know what the variables are I'm measuring here, just numbers. So the dependent variable is on this y-axis. Along the x-axis here, I have independent variable A. It has two levels, A1 and A2. And then I have these two lines for B1 and B2. First of all, if you look at that, you can tell me that B1, is that right? Yes. B1 is lower than B2. So B2 is bigger than B1, right? We can just see that. But B2 is bigger than B1 by a little bit at A1 and a lot at A2. It's kind of hard to talk about the effect of B without mentioning the effect of A, without mentioning the other variable. I think I can here. I think I could say generally, sure, B2 is bigger than B1. Yeah, I can say that. But I also, if you ask me, is it the same all the time? Oh, no, it's way bigger at A2. Like I have to throw in that qualifier still. I think I can still generally say that B2 is bigger than B1. But you can see what we have here is an interaction. The effect of B changes depending upon the level of A. It's bigger at A2 than it is at A1. Okay? Yes? Questions on that? Does that explanation of what an interaction is make sense? Yeah? Okay, good. This is good. This is good. It's going good. The difference between B1 and B2 is smaller at A1 than it is at A2. Again, that's what an interaction is. Okay? Another way to say that is the effect of B changes upon the level, depending upon the level of A. I wish that wasn't on top of it like that. I should have moved, oh well. Putting in all my flames and stuff, I never thought of moving the graph out of the way. Like I said, the example that I tend to think of is the fact that it's harder for black women than it is for white women, or white men. It's depressing. If you can think of a happier one that things get better for people, maybe that'd be nice. Anyway. So again, x equals mu plus alpha plus beta plus epsilon. So this is going to have assumptions. Right? This stuff always does, right? We're going to have assumptions of our model. We're going to have assumptions. It's going to be an F test. Actually, it's going to be 3 F tests. So the model has some assumptions. Our first assumption is that the sum of all the treatment effects for A equals 0. I will look at this practically in a moment. First, I'm going to show you this with notation, and then I'll show you it practically. So, and the sum of the B's equals 0. Alpha I, beta j, that means A1, A2, A3, B1, B2, B3. The 1, 2, 3s are the I's and the J's. You'll probably see me shortly just drop using those. I'm just going to ignore them, okay? This is not a math class. And the sum of the alpha I, beta j's, the interaction effects, must equal 0. You'll see shortly that they will and they must and they always will, and it is a property of the universe that they will. While this is an assumption of the math that's behind this, the world works like this and it can't not work like this, which is pretty freaking cool, actually. Oh, an error is normal and independent with a mean of 0 and a variance of sigma squared. The only new thing here is that we've thrown in this interaction assumption. This is just the second main effect assumption. Before we just had sum of the tau, the treatment effects equals 0, and then the error. So all we've done is added in a new variable, that's B, and then we've added in the interaction term. It's the same thing. So you'll see in a moment, like I said, that will always happen anyway. You can't even make up data that don't do this. It can't be done. It's because of the way numbers work. The beautiful thing about this is, then that means you know that when you make a mistake, you know it was your mistake. You can't be, oh, I wrote the number, yeah, I wrote the number down wrong or something. But it can't actually, or made a mechanical error, because this has to happen. Not the normal independent part, but the summing to 0 thing will always happen. And again, you'll see why in a sec. So, and then of course there's going to be an F test, and in fact there's going to be 3 F tests. There's going to be one for A, one for B, and one for AB. So there's going to be a main effect of A F test, a main effect of B F test, and an AB F test. So what are our assumptions for F? Well, these are all ones that we know about. Homogeneity of variance, so that means all the variances are the same. And you know, practically that means one isn't 4 times bigger than any of the other ones. Random samples. Yeah, sure they are. We can violate the shit out of that. It doesn't matter, man. We can violate random samples. We do it all the time. Hope some of you guys have signed up for some of your classmates' honors thesis projects. There are posters on the LMS with QR codes telling you, hey, be in my project. And a lot of these things take 5 or 10 minutes. Do you think any of those are random samples if we're just asking random? It seems like I'm asking random people. Are they random people? No, they're people only who are taking classes from Dave Broadbeck. That's not even close to random. But it doesn't matter. Stats still works. It's very cool. It has the random samples for the math to work. But it turns out, for all the assumptions of the math, but it turns out, in fact, that you can violate the crap out of this. The way you prove this is through something called a Monte Carlo experiment. So you actually know the whole population and you generate data sets. Anyway, it doesn't matter much, to the point of no one cares about random sampling. Normal populations, we also don't care about that, because we're dealing with sampling distributions. They'll be normal, so who cares? We don't have to worry about that. It's more accurate if they are, but the difference is so little that it doesn't matter, so we don't care. That camera, getting on my nerves. I think if I threw it, I'd probably get in a lot of trouble. So I'm just going to move it over. All right. So those are the assumptions that we make for the F tests we're going to do. We have to do 3 F tests. We do one for A, one for B, and one for the interaction. All right. These are numbers. Oh my God, actual numbers. These are the examples that I think will show you that these things always sum to 0. They must. So this is a numerical example. Now, we have 2 variables, A1 and A2, A and B, and they each have 2 levels, A1 and A2 and B1 and B2. This is a 2x2 experiment. Now, these are meant to be 9, 7, 3, and 1. Those are meant to be cell means. So there's supposed to be other numbers in there that make up that average. So there's like subjects in each of these groups. There's 5 people, let's say, in each group. But I don't need to show you that to give you this example. So let's just start out by thinking. We're doing this from first principles. So let's think about this. X equals mu plus alpha beta plus epsilon. Let's take out the grand mean. The thing that applies to all of them, the grand mean is the same for everybody. Right? It's the same for everybody. So let's figure out what it is and subtract it to see what's left over, to see what the deviations are that are left over. So what we have to do is figure out the grand mean, which is not that hard. 9 and 7 and 3 and 1, and 9 and 7 is 16, and 3 is 19, and 1 is 20. 20 divided by 4 is 5. I got that by adding all of these up and dividing by 4 because there are 4 numbers there. It's funny, people sometimes look at this like it's some kind of magic thing. It's like, no, I got the average of 4 numbers. That's all I did. There's nothing remotely complicated here. I have 4 numbers, I want the average. I add them together and divide by 4. And I cooked the example so it's even number. Right? There's no decimal. So what I'm going to do now is I'm going to remove 5 from each of those cells. Once I've done that, the only things left, now look at the model, the only things left are alpha, beta, and alpha, beta. We don't have epsilon there. Like I said, I haven't put individuals in. I'm just using averages, okay? All right, so questions so far? This is actually what the math does. So I took 5 out of each cell. 9 minus 5 is 4. 7 minus 5 is 2. 3 minus 5 is negative 2. Right? 1 minus 5 is negative 4. Now, I said that I took out the average, which means that the only thing we have left are deviations. And those deviations, right, because they're just the alpha i's and beta j's. Remember I said they must sum to 0? They always will sum to 0, and they can't not sum to 0. Oh, look, the numbers sum to 0. And you might think, Dave, you just said you cooked this example. I did. You can use any 4 numbers, it'll work. When you take out the average, you'll just get what's left over will be deviations from the average. By definition, it must be. So and you will be doing these little example things. These are the kind of things I like using these as quiz and test questions. So learn how to do this, is what I'm saying. If this ever comes out after you've taken out the grand mean, you go, oh, these numbers don't sum to 0. You did it wrong. It can't come out without it summing to 0. It is literally impossible unless you made a mistake. You cannot come up with 4 numbers that'll do that. You can't. The world doesn't work like that. So what we have left now is just the alphas, the betas, and the alpha betas. We have no grand mean anymore, right? It's gone. We removed it. So as I say here, with the grand mean removed, we can now go on to the effects of A and B. Let's do the effect of B. So B1, the effect, let's see, B1 raises scores by 3. B2 depresses scores by 3. How do I know that? Because 4 and 2 is 6, divided by 2 is 3. Negative 2 and negative 4 is negative 6, divided by 2 is negative 3. Why did you divide by 2, Dave? I was getting the average of 2 numbers. Like, it is really, really, really simple. I think people want to make this harder than it is. 2 numbers, so we divide by 2. Like, it's really one of those things. I think people expect that this to be a lot harder than this, and it's not that hard. But with that said, questions. You see what I did here. Okay, you see what I did. Okay, so what this is called collapsing across A, because we basically collapsed the whole thing. So now we take out 3 from all the B1s, and we're going to take out negative 3 from all the B2s. 4 minus 3 is 1, right, etc., etc. Now, let's double check that we haven't made any mistakes. This should still all sum to 0. It does, good. What else? Oh, let's see. The b's should now, there should be no b effect. 0, 0. Oh, good. So the b's are gone. The a's are gone, the b's are gone. I'm sorry, the b's are gone, not the a's yet. For A1, it averages out to 1, and A2 averages out to negative 1. I am now going to say literally the simplest thing I will say ever teaching a university class. 1 and 1 is 2, divided by 2 is 1. Okay? Here it's a little bit harder. Negative 1 plus negative 1 is negative 2, divided by 2 is negative 1. There's a negative there, it's a little harder. This one time, it was about maybe 15 years ago, I was teaching this, literally at this point, and I'm walking along, and the president at the time of the university walks by, and I'm saying, so 1 and 1 is 2. And I looked at the guy's name was Rick. I said, this stuff's way harder than it is normally, Rick. We're doing arithmetic. That's all this is. So we're going to take 1 from all the A1s. You should probably see what's going to happen here. When we take the 1s out of here and the negative 1s out of here, it's going to be a bunch of zeros, isn't it? Right? So we're going to take 1 out of the A1s and negative 1 out of the A2s. So we're going to do the same as we did before, but that's for the A's. So we get that. Well, I think those sum to 0, so we clearly haven't made any mistakes there. Well, there's nothing left, so there's no interaction. Because the only thing that's possible to be left is an interaction. These are all zeros, we have no interaction. If they were non-zero, we would say we have an interaction. But they're not non-zero, they're 0. And with them at 0, we just say there's no interaction. Okay, questions so far? Does anybody want me to go back and show you what we did? Does it make sense so far? I just want to make sure it's making sense. Yeah? Okay. Okay, good. So let's remember I said pictures worth 1,000 words. Let's look at it. Oh, look, here's a picture. Beautiful. We graphed it out. In fact, if I was doing this, I'd probably graph it first. Let's see. No interaction. The effect of the B effect, which is that what? B1's bigger than B2. It's by the same amount at A1 and A2. And I can tell you by looking at that A2 is lower than A1. How can I tell that? The average of A2 is just between these 2 points. The average of A1 is between these 2 points. This is higher up than that. Like, it's nothing fancy. To determine significance, it gets a little fancy, but let's not worry about that right now. Let's just get a feel for this. And by fancy, I mean you have to divide a couple numbers. It's not that complicated. Okay. How about another one? Some more numbers. This time it's another 2 by 2. So going across, 20, 0, negative 10, 2. A1, A2, and then B1, B2 down the side. Let's get that grand mean again. 20 plus 0 minus 10 plus 2. Let's see, that's 12 divided by 4 is 3. Okay. I'm going to tell you that I typically use examples like on quizzes and tests and stuff where the numbers work easily to do in your head. Whole numbers, etc. Just letting you know that calculators are fine things, but you should be able to go 20 minus 10 plus 2 divided by 4 is 3. Like, you should be able to do that. So let's take it away. Let's take the grand mean out. So that's the grand mean of what is it, 3. So we're going to take 3 out. And now again, let's look at this. Let's figure out what it's going to be before we look at the next slide. So 20 minus 3 should be 17. 0 minus 3 is negative 3. Negative 10 minus 3 is negative 13. 2 minus 3 is negative 1. Okay. Okay, let's see if that's what we got. I'm assuming I did it properly. Yeah, I did. Okay, good. So now we have that. So now we're going to do the A and B, the A's and the B's. And I guess I decided to do the A's first. So when I sum B1 and B2, I get 4 and B for A1. And at A2, when I sum B1 and B2, I get negative 4. Again, these will always mirror each other. If there's 3 of them, you might get negative 2, negative 1, positive 3. That still adds up to 0. Okay? So it just has to sum to 0. They aren't always just going to be negative 1, positive 1, negative 2, positive 2. If it's 3 or 4 or 5 or whatever groups, it's still going to sum to 0. Again, note how they always sum to 0. Every single time you do this, you should be looking like sums to 0, sums to 0, sums to 0. Just so you, and if it doesn't, you made a mistake. There's no other way about it. You made the mistake if it doesn't sum to 0. Because as I hope you can see here, it just has to work that way. Okay? So what we're going to do is we're going to take 2 out of all these. We take negative 2 out of all these. So I think I just did that here. I did. So we end up with what? 15, negative 1, negative 15, 1. Okay, so it's interesting. First of all, the cells all sum to 0, which they should. And so do the columns sum to 0, because we've taken out A. Right? 15, negative 1, 1. However, the rows don't sum to 0 yet, because we still haven't taken the row effect, the B effect, out. So we get 15, negative 1, negative 15, and 1. Now those both sum to 7. Or sorry, sum to 14. Divide by 2, we get 7 and negative 7. Questions so far? You guys are good. You guys are writing stuff down and paying attention. That's all I ask. But if you have questions. Okay, good. Let's take out, so we're going to take out 7 from all the B1s. What are we going to get? Take 7 out from all the B1s. I'm bruising my tailbone. It's unpleasant. So let's see. We're going to get 7. Okay. Well, let's do that right now. 8, negative 8, negative 8, 8. Oh, this time. This time, I think we have something left over. We have an interaction this time. See, I hope this helps you understand what the interaction is. It's extra stuff. We've taken out the A effect. We've taken out the B effect. But there's still this left over. It still sums to 0, which it has to. It must. But it's non-zero. And if it's non-zero, we then say we have an interaction. If these were all zeros, we go, well, that's no interaction. Just like that. The last example was all zeros. Right? This example is not all zeros. Okay. So again, now the effects sum to 0 in every possible way, up and down, left and right. But the effects themselves are non-zero, so we have an interaction. By the way, sum of squares for interaction is, let's see, 256. How did I do that? I squared 8, and I squared 8, and I squared negative 8, and I squared negative 8. 64 and 64 and 64 and 64 is 128, 128, which is 256. Those are deviations from a mean. We've taken it out, so they're deviations from 0. So I square them, sum of squares. That's the sum of squares for interaction in this case would be 64, 100, 256, yeah. So that's actually what the thing does. It's isolating. That's what the math does, is it isolates the effect of A, B, and AB. You can see this one. Oh, you can see there's an interaction there. So this is a weird one. Because if you look at this, I think I can say that, boy, there's a big effect of B. B is way bigger than A1, than A. Sorry, B, what am I saying? B1 is way bigger than B2 at A1. At A2, they actually flip. They're almost the same at A2. Or there's a small effect, but it goes the other way. And the average for B is, what did you write there? There's probably an effect, B, I don't know. B1's probably bigger than B2, but, well, it is. The math shows that, but it's hard to talk about it, isn't it? Like, I can't really comfortably say that A1 is bigger, or sorry, A2, yes, is bigger than A1, or A1 bigger than A2. I can't because I have to mention B. It's very difficult, in fact. It's very difficult to do that. Yeah, it's almost impossible. Yeah. So when you're interpreting an interaction, it's kind of hard because interpreting main effects, that's what the effect of A, the effect of B. In the presence of interactions is hard. In fact, it's fraught with bad things. Because if I say that A1 is bigger than A2, and the math shows it, that's fine. But if then I have to always qualify it with except at B2. Yeah, A1's always bigger than A2, except at B1 where it's the same. Then it's not always bigger. Like, I don't feel comfortable. The math says it's bigger, that's fine. But the math is one thing, my interpretations as a scientist is something else. So I gotta look at that and go, do I feel comfortable talking about this? Right? So with what's called an ordinal interaction, that's pretty easy. So an ordinal interaction is an interaction where the order of the main effects is preserved. So let's draw you one here. Oh. Of course, the switch to make this go up is all the way over here. That makes complete sense. I just want to draw some stuff on the board. Yeah, because getting one that just does that with your hand, which that's got a bunch of points of failure in it, we'd have to pay a bunch of money, or we could get that. Anyway, mechanizing everything doesn't always make it better. So if you're let's see, if I draw here, is it good? People can see here? Yeah? Okay. So if we've got, so there's A1, whoops, A2, and we got our dependent variable here. So if we've got, here's B1 there, there's B2. So if you look at that example, yeah, that's not bad, right? I can look at that and say, sure, B2 is always bigger than B1. I'm comfortable saying that. I would say it's bigger at A2 than it is at A1, but B2 is bigger than B1. Okay? So that's what's called an ordinal interaction because the order of the main effects is preserved. On the other hand, if we have what's called a disordinal interaction, if I go down here, you see that? Down there, is that okay? Okay. You can't just nod, I can't see your faces, eh? Okay, somebody has to say something. It's good. Thank you. No, thank you. No,
Favorite
seriously.
action.
No, yes, that's right. No, thank you, because I know some of you aren't used to me, and literally, I can see you, but I can't see your. I mean, I kind of see your faces, but not so much. Anyway, so if we go A1 here, then A2 here. Now this is going to be what's called a disordinal interaction. So we'll go like that, and like that. So that's going to be B1. That's B2. Now we can see here, with the second example that I've drawn up on the board here, is that A2 is higher than A1. Yeah, and in fact, it looks like probably on average B2 is higher than B1. Would you feel comfortable talking about them in isolation? Well, the lines cross, for Christ's sakes. You look at that and go, how can I talk about the effect of one variable on its own when the lines of the graph actually cross? I can't. I can't talk about that. So in this case, it's hard to interpret main effects. In this case, you probably just talk about the interaction. There are times, I've colleagues, friends around the world who actually only look for interactions. They don't care about main effects. They want something that just crosses like that. And that can't happen in certain cases. So you will hear some people, I think, in fact, the textbook, well, I know the book talks about it a little bit. It is the case that some people say do not interpret main effects in the presence of any interaction. I think that's a little bit too much, a bit too far, but this is just my own personal opinion. I like to take those kind of things on a case-by-case basis. If I feel comfortable theoretically and also statistically and based on my results talking about one thing in the absence of something else, then it's fine. So I kind of trust the individual scientist more than I trust some hard and fast rule. So that's my view. Let's take a picture of that so I can put it on the log. There we go. All right. I hide things. Where did I put my mouse? There it is. The number of times I put it down somewhere and think, oh, that's a great place. I'll certainly remember that. And it's always some weird place, like underneath a monitor. See, people think I'm smart. I went to school for a long time. So that disordered interaction, it's almost impossible. I don't know how I would talk about the bottom graph here. I just don't know how I could do it. I just don't know how. But I think the idea of never talking about main effects in the presence of interactions is too far. And that's my view. Not everybody agrees with me. Like I said, I think taking it on a case-by-case basis is much more sensible. Okay. So let's stop for a sec. Questions? So far this is okay. Yeah, this is good. Thank you. Okay, so far we're okay. I like that. So let's keep going. Let's partition the degrees of freedom and the sums of squares, shall we? So, okay, remember the model. I make little jokes for myself, and I figured they're not that funny, so I don't say them out loud. So let's go back to our model, and what's our model say? Our model says that x equals mu plus alpha plus beta plus alpha beta plus epsilon. Starts talking with Greek letters and talking about mathematical models, it scares most people away. Now, a person probably couldn't see there that it was probably looked like it was doing people, because there's not. I thought, oh, I'll just come in because Dwayne's got his stats class next. No, it's okay. I don't care. People want to come in and get frightened about what they're going to have to take next year. Right.
Running with fear.
That's right.
Greek letters.
All right. So if that's the case, well, let's think about this in terms of sums of squares, right? Deviations from the mean. So sum of squares total should equal sum of squares A plus sum of squares B plus sum of squares AB plus sum of squares error. And you might say to yourself, Dave, where is sum of squares for grand mean? And my response to you would be, what would they be? what does R mean? How much does all of our average deviate from our average? Well, 0. So we just don't even, it'd be stupid to have that there, right? So we don't have that there. But this is basically, deviation is A, B, epsilon. And this here just would be, there's no deviations here, so we're going to So we're going to partition the sums of squares, and the degrees of freedom will follow along with it. Right? That's how it goes. Okay. So think of it this way. Sum of squares A is the squared deviations of column means from the grand mean. Do we have enough people to make a pretend example of an experiment here? 10. There's too few people to think of. Well, it doesn't matter. So we've got a group, we got different groups of people, and we got, if we look at A1 and A2, we would say, let's say the column mean is 10 and 6. I haven't taken out the grand mean yet, so they don't have to sum to 0. Then we figure out what the grand mean is. 8. It has to be. 10 minus 8 squared, 6 minus 8 squared. Deviations, and then we add those together. So it's going to be 8, right? 2 is 4, 4 squared twice. Yeah. So they're deviations of the column means from the grand mean. Sum of squares B is deviation of the row means from the grand mean. What we're basically doing is we're taking a variance of a bunch of means. There's a reason this is all called analysis of variance. So that's the square deviations of row means from the grand mean. There's the strangest set of stuff up here. It's getting into March, and this is a whole year now of accumulation of crap. It's kind of great. Now, sum of squares AB, that's the new one. Sum of squares AB, that's the interaction term, is square deviations of the cell means from what you would expect if there were only effects of rows and columns. It's the extra stuff. The stuff that's left over at the end after we've taken everything out. Remember 8, -8, -8, 8? The stuff that's left over at the end, all squared and added up together. That's all it is. And sum of squares there is square deviations of each individual score from the cell means. And again, we didn't have individual scores because it just makes doing this, we'd still be doing the first example. And it wouldn't help anything. So there's individuals in each group, and they have a mean of their group, and it's their deviations from their group mean. Their group or their cell, as it's called. So more precisely, we can actually write this out. If you look at what this says, it actually says all the things I just said in words, just in mathematical notation. That's all this is. Sum of squares total, I almost started drawing on the thing. That would be bad. A colleague did that once when we first got the whiteboards, which was about 15 years ago, when we moved off from blackboards to whiteboards. Somebody brought a Sharpie in, like a permanent marker. You're not supposed to I will say I've also drawn on the wall once, so it also all balances it. So, each score minus the grand mean squared. That's going to be the sum of scores total. You see on the left-hand side, that's the sum of scores total. So let's look at this now. Sum of squares for A. So look, that's the J, that's the column means minus the grand mean. The row means minus the grand mean. What are P and Q? It's the number of levels of A and B. Don't get worked up about that. Seriously, like don't get too bogged down in the notation. What this is saying here is, look, you take a score, you subtract the row mean, you subtract the column mean, and you add the grand mean back in. Why do you do that? Because the grand mean and the row mean and the column mean are made up of the grand mean, so if you do it twice, you got to take it out once. Okay. And then finally, this is just individual scores from their cell mean. Really, again, this is just the same thing. It's the same as before. The new part is here, the interaction term. So the total number of degrees of freedom, of course, for any design is the number of observations minus 1. So on the left-hand side, we have n minus 1 degrees of freedom. Big N minus 1. So to get the mean square, well, you don't do mean square total. But. So let's look at it for A and B. This is A, this is B. So if we have two groups, let's just say we have just two. And the effect at A1 is 3. What's the effect at A2? They have to sum to 0. The effect at A1 is 3. What's the effect at A2?
-3.
Yeah, it must be. Okay, what if it's, so that's, let's see, that's 2 degrees of freedom. That's 2 groups. If we got 3 groups, the effect of the first, let's do it on the board, so it's complicated. 3 groups. So if it's 7 and 26, what's the final one? Yeah. Minus 33. Is that right? Yeah. Because it has to sum to 0. Oh, now it's 3. Now it's 2. Oh, you just lose a degree of freedom. So it's the number of levels of A minus 1. So that's easy. Which you tell you probably that's going to be B minus 1. There's no way it's going to be any different. Now let's think about this for the interaction. So for the interaction, if we've got a 2 by 2, if we put 1 here, that now fixes all the other ones, doesn't it? Because it's like -1, -1, 1. We have 1 degree of freedom with a 2 by 2. Is there an eraser? Please tell me there's an eraser. Yes, there is. Let's add on a 3rd level. So let's see, we'll put a 2 here, we'll put a 6 here. Uh-oh, that means that's -8, which means that's 8, that's -6, and that's -2. Looks like I had 2 degrees of freedom with a 2 by 3. I assigned 2 numbers and then I couldn't do anymore. If I have an 8 by 8, I can guarantee you that I have 49 degrees of freedom. Because frankly, it's pretty easy. It's just A minus 1 times B minus 1, and 8 by 8 is 7 times, so it's 8 minus 1, 7 times 7. So that's A minus 1 times B minus 1. That's A minus 1 times B minus 1. That's the number of degrees of freedom you have for interaction. And finally, for error, you have A times B times N minus 1. N minus 1 is the number of subjects in each, little n is the number of subjects in each group. You lose a degree of freedom in each group, and you have A times B groups. Right? is A times B groups. Okay. Questions so far? Okay, maybe one more. It starts to get incredibly deep shortly. Okay. So if you remember when we tried to figure out what we divide by what to do in regular vanilla analysis of variance, we figured out the expected value for mean squared treatment was treatment plus error. We divided by mean squared error. The expected value is error. So we have to look for the expected values of these mean squares to figure out what we divide by what to know how to find out if we have significant effects. I just said that right there. Why didn't I reveal that first? No. So, as it says here, and as I will say again, remember for the simple ANOVA, the expected value of mean squared treatment is error plus treatment. And the expected value of mean squared error is error. So we must divide mean squared treatment by mean squared error to find out if we had an effect, how much extra variance there is there. So we're going to have to do the same thing here. We're going to have to do it for A, for B, for AB, and actually for mean squared error. Figure out the expectance. Well, figure out. I'm going to tell you what they are. This was one of those things that they used to actually have tables in the backs of books tell you how to figure out expected values of mean squares. They just don't have those anymore. Okay, I'm going to show this slide, and I think we're going to stop after this one because it gets weird. Okay. Maybe doesn't want to move. What's going on? There we are. Okay. So the expected value of mean squared error is the alpha plus epsilon, treatment plus error. Great. For B, it's beta plus epsilon, the effective B plus error. Tremendous. That's easy, it's sensible, it makes complete sense. And of course, the effect of mean squared AB, the expected value of it, is alpha beta plus epsilon. Again, so exactly what we would expect. And the expected value of mean squared error is epsilon. I hope you can see what we're going to do here. So we're just going to take mean squared A, divide by mean squared error. Mean squared B, divide by mean squared error. Mean squared error AB by mean squared error. And that's going to give us the effective A, the effective B, and the effective AB. So we're going to do 3 f-tests, but all 3 of them have the same denominator for the fraction, which is mean squared error. All right, questions so far? All right, I know it's early, but we're stopping now because it starts, I know this is a lot. And I think it's only fair that I don't destroy you. Just try to take it easy. So again, so we divide all by mean squared error to isolate the effect. Okay. All right, we'll pack this in for today, and we will talk more about this stuff on Wednesday, okay? And we'll finish it up then. And for those of you watching the YouTube video, I'm about to go to a very short break, and you won't even notice it. Somebody, yeah.
I got so many spam calls.
All right, so if you're watching this on YouTube, obviously we just got back to the next class. Right, so this is where we left off last time, and the idea of getting the expected values of the mean squares for the 3 f-tests we're going to do. So there's going to be one that's going to be expected value of mean squared A is just going to be alpha plus epsilon. B is beta plus epsilon. AB is alpha beta plus epsilon. And error is epsilon. This is pretty easy, so what we're going to do now is just divide mean squared A by mean squared error, mean squared B by mean squared error, mean squared AB by mean squared error. As you can see, that isolates the treatment effect we're interested in. So all because the E's cancel, basically, the epsilons cancel. So we are left with alpha, beta, and alpha, beta. So we see the size of the effects. Okay? So that's all, I don't know, I think pretty intuitive, frankly. Right, so that's, yeah, I think this is pretty intuitive, and it's, let me just talk. Okay. So now, of course, that's why I stopped there, because it starts to get weird. That's why we stopped at this slide last time. And that's because things get a little strange. Those expected values are based on a series of assumptions, like any other mathematical thing. And one of the assumptions is you're only interested in those particular values of A and B. So when I say that, I mean if you were doing the retention interval experiment, you're only interested in retention intervals of, what did I say, 5 minutes, 1 hour, 24 hours. But you aren't interested in 23 hours, 6 minutes, an hour and a half, that all you care about are those 3 points. Right? And no others. No others, just those 3. And if that was the case, then what you shouldn't do, just looking for, oh yeah, my markers are here. Need a point of bringing markers, there we go. So what we tend to do, remember, you think of presenting data, we'll often do a nice graph, and we'll show, well, let's do that, retention interval here, and percent correct here. You know, we got 5 minutes, 1 hour, and 24 hours. But we wouldn't normally just put those 3 dots, we'd probably join these, wouldn't we? And if we join those, we're now implying to people that we can make statements about other values. I don't know, we can. And the math says actually we're not supposed to. What? That's a weird thing to think, isn't it? Because no one's ever told you that before. But the math actually is based on the idea that you're only interested in those levels. And that's not going to be good, is it? This is what's called a fixed effects model. Okay. Fixed effects model. The effects are fixed. They don't move around. Okay. All right. All right. Good. What if we randomly chose levels? And I mean actually randomly. I don't mean like, that's so random. I mean like literally random, like using a random number table or some such. Okay, so not in the popular parlance sense of random, in the actual mathematical sense of random, if we actually literally randomly chose levels. That's also something we don't do very often. In fact, you'll probably never do this. But what if we did it? A random effects model, the expected values change, and you're like, what? Yeah, because there's now another source, I'm not going to call it a source of variation, but there's something else we have to take account of, and that's the fact that we have different, that we have another sense of randomness in there. We have to sort of model that as well. So it turns out that the expected value of mean squared A now is alpha plus alpha beta plus epsilon. B, well, you can probably guess, is beta plus alpha beta plus epsilon. The interaction is still out of thank whatever deity you would like to pray to. By the way, those of you who do have deities, could you maybe pray to them about enough with the weather? Okay? I don't do the praying, but if you're into it, could you please have them deal with the weather? That's all I'm just asking for that. Just tone it down a little. Just tone it down a little. Right. Alpha, beta plus epsilon. A friend of mine a couple years ago I said that, and she said, well, I had a cigarette and I threw tobacco on the ground. She's indigenous, and she said, so I guess it's my fault. That was pretty cool. Expected value of mean squared error is just epsilon. Okay, we can probably work this out happily. So you can see now, I hope, and I'll work it through with you. We're going to take we're going to take mean squared A and divide by the interaction. Ever weird? Because what that does, there's alpha, beta, and epsilon, alpha, beta, and epsilon. We want to isolate one source. Oh, alpha, that's what we want. So we're literally going to divide mean squared A and mean squared B by the interaction mean square. The interaction will divide by error. You can see that here. Right? Okay? Does that make sense? I'm not saying the fact that these are like this makes sense because that involves more math than I'm willing to do. But what we divide by. Does that make sense? I hope so. Yeah? Okay. Because you're always just trying to isolate the thing you're interested in. So just the alpha beta for this one, just the beta. Okay? So it's pretty rare we're going to randomly choose all our effects, but our levels, I suppose we could. Okay, then we can have, obviously, there's one other way we could do this, is a mixed model. Now, if A was fixed and B was random, this is not a typo. You might be looking at that saying, well, if that's the fixed one, shouldn't that be alpha? No. Turns out no. So if A is fixed and B is random, A is alpha plus alpha beta plus epsilon, B is beta plus epsilon. Happily again, the interaction term and the what we call mean squared error, they stay the same. So you see what you're going to do here is you're going to take mean squared A and divide by the interaction, but mean squared B by the error. Now, you might be thinking to yourself, Dave, how do I have to remember all this stuff? No. Because what you can do is you can tell SPSS, that's a random factor, that's a fixed factor. You cannot do that in PSPP. If you do it in PSPP, you're going to have to remember this. So you just make sure you have this available and say, oh, if I have to do an extra division or something, if I have to do something by hand, it gives you the mean squares, they're fine, but it might give you an asterisk for the F, which means I couldn't calculate it. All you do then in that case is you just redo it yourself using a calculator. It's no big deal. And like I said, this is not a typo, and it's counterintuitive. It's just the way it is, okay? All right. Like, I don't mind the winter. I kind of like it. I just, on the other side of the break, I don't want snowstorms. That's to me. It's the other side. When you get to the other side of the break, I want it to be starting to be going the right way towards being nice out. Okay. Maybe I'm obsessing a bit over this. Questions so far? So you think to yourself, when the hell would we use a random factor? Well, let's think about this. Let's say here's an example, and this I think is the example in the textbook, but it's an example that everybody uses. Because it's a good one, and that's, let's say we were looking at two different kinds of tires. So winter and summer tires, we know about that here. And we wanted to test the wear of the two different kinds of tires in different places in Canada. Well, I don't know about you, but again, I've been talking about the weather. Maybe that's why. It's different here than it is in Victoria, BC. Right? They don't need snow tires there. No. It snows like a couple of centimeters and the whole world shuts down. Right? And that's understandable. They don't get a lot of snow. Don't make fun of them. You make fun of them for other things. I don't like making fun of people for their weather. I think it's right. Here, we get a lot of snow. But the snow you get here a lot of times is it's very cold usually here, right? Or Edmonton. Let's go colder and bigger. Let's go to Edmonton. Really cold. Very little of that sort of slushy kind of snow. It's just cold, man. And then let's go somewhere where we get that sort of slushy snow. Let's go to Corner Brook, Newfoundland, where I used to live, where we would get literally 4.5 meters of snow a year. You have no idea what snow is. You think you do. I'm from Sault Ste. Marie. You have no idea what a lot of snow is. Fine. That's 3 different places. How am I going to pick? So I just think I pick by different amounts of snow. If we're looking at snow tires, we couldn't use Canada. We can't even use those individual cities. We want to have a random sample of cities. That's what you do. So in that case, one of our variables would be the city. So we have, Sault Ste. Marie and Edmonton and Victoria and Corner Brook, Newfoundland, and Boucherville, Quebec. Because then we can go see my brother-in-law. He's a good guy. My sister-in-law, too. They're great. Wonderful people. Okay. There you'd randomly select the levels. Because I want it generalized to Canada. In fact, I think that, as I said, I think that's the example they use in the book, is about tire wear. But winter and summer tires are a fixed factor. We have those two kinds of tires, but then we're going to look at, so that's factor A. Let's see, what I have here. So if A is fixed, yes, A is going to be winter tires and summer tires, and B is cities in Canada randomly chosen. And then our dependent variable in that case would be tire wear. Okay, so in that case, you would use random factors. We don't use them a lot, except under one very specific circumstance that we will get to next week. Okay, but I bring this up for an important reason, and again, as I said, you'll see more about it next week. But the idea here is that you're randomly choosing the levels of a variable. If you're not randomly choosing it, just go default to fixed. Okay. But if you are randomly choosing it, or something close to random, go with the random effect. So the thing is, what's the upshot of this? For our purposes at this point, with just a simple, factorial ANOVA, we're assuming the random effects model, the levels of the random factor are randomly selected and independent of each other. So if I've chosen Corner Brook, Newfoundland from my hat, which had Canadian cities in it, it doesn't make a difference. If I know that I chose Corner Brook, it doesn't mean more or less that I'm going to get Sault Ste. Marie or Edmonton or Victoria or wherever else. What we're normally doing is kind of a sort of kind of mixed model. And the closest thing to that mathematically is a fixed effects model. So that's the analysis we tend to use. But we really are violating the assumptions of the model whenever we try to interpret other points rather than just the ones we're interested in. So this is always, to me, the key thing. Did you actually randomly select your levels? If you randomly selected your levels of your independent variable, then yes, you have a random effect, and you should be using a random effects model. If you didn't use random sampling or something like it, right, then it's a fixed effect and just treat it as such. So you'll find that we always treat things as fixed effects, except for one key variable that we will get to next week. So it's very rare that we ever deal with this. People are starting to care about this, which is great. For the longest time, people didn't care at all about this. They just said everything's fixed and went from there. And the problem with that is that it's not true. Sometimes we did randomly choose some levels. So you'll in the last 5 years, and I don't know what did this, but in about the last 5 years, people are starting to worry about random and fixed effects, which is kind of great. Because it just makes people's stats more accurate. So, good on them. A buddy of mine emailed me about 5 or 6 years ago and said, one of my graduate students wants to analyze her data like this. Is this right? Because I was the TA for graduate stats when he was in the class that I was TAing. He's my best friend from grad school. So statistical questions, he still default to me because he knows me. So I replied to him, did you actually pay any attention in stats 30 years ago? And he's like, no, I didn't. Weren't you the TA? Oh yeah, right, okay. So I told him, no, this is right. It's a random effect. It's great stuff. So we're starting to care more about it. If you go to grad school, you probably will hear more about this. It's not really as important for us. Okay, so we get a summary table. And remember the famous summary table for the one-way analysis of variance. So we had one on our quiz recently. Well, this is the same kind of thing, except now we have a two-factor model. By the way, keep in mind that is for fixed effects only. But unless I tell you it's a random effect, it's a fixed effect. The way to look at it is, unless somebody told you that you were selecting levels of a variable randomly or pseudo-randomly, they weren't. Just think of them as fixed. So, source of variation, the same thing we've seen before. And again, this looks exactly the same, except it's got, two independent variables and an interaction term. A minus 1 times B minus 1 for the reason. Okay. So this changes if these are random effects, right? So because the error term, the thing you divide by in analysis of variance, would change if these were random effects or if this was a mixed model. It's not a mixed model, it's a fixed effects model. Always assume it's fixed effects unless it's clearly stated that it's not, basically. Okay. Questions so far? You good? Yeah, good so far? Okay, this is good. I'm really glad. This is great. Smaller group this year, so it's going more quickly. I don't know. Seems okay. By the way, let's go back. Let's go back one. You know that? Boy, does that ever make a good test question in about a week and a half. Just saying, you should know how to do that. And didn't I tell you that those kind of tables are great ways for you to test about 15 different things at once? So, yeah. If you can look at that and it makes sense to you, you don't even have to study. I shouldn't say that. At least you have to study doing those. Because if this makes sense to you, you'll be able to sort of figure out if there's, with blanks and stuff, you should be able to figure that out, no problem. Okay. So now let's go forward again. Remember again, that is only for fixed effects, but if in a question like that, I would tell you. So if it was one of those, it was a question like this, and you will get a question like this. As I told you before we started recording, there will be a summary table question on the final, or the next test or section. But I will tell you if they're fixed or random effects. Yes, Jay?
Okay, so for the F on that one, so like if it's the fixed effects only, you only do those like calculations. But if it's not the fixed effects, it's going to be different.
It'd be different. So if it was random effects, you'd be dividing mean squared A by mean squared AB, mean squared B by mean squared AB, and mean squared AB by mean squared A.
Okay.
Yeah, so you just go take a look at those expected values that are on the slide, and it should tell you what to divide by what. Yep. Yep. Like I said, I will tell you explicitly on a question like that, because that's not testing anything if I don't tell you explicitly. It's just me being a dick. It's like, as I think I've told many before, I don't do trick questions because I don't have to prove to you I'm clever. There's letters after my name. They mean Dave's clever. Oh boy, these designs can get big. This isn't bad. This is a three-way design. 2 by 2 by 2. We have, let's see, let's think of a case where we have that. Oh, sure. So we have memory. We'll use our memory things again. So B1 and B2 would be, let's see, B is going to be retention interval, short and long. Don't worry about the numbers. Let's see, what's A going to be? Oh, recognition and recall. Different memory test types. Both testing the same kind of memory, which is an explicit type of memory. We'll just use recognition or recall. Okay, that's good. And C would be, okay. Mass practice for C1, distributed practice for C2. So C1, they see each word for 15 seconds. C2 gets them at 5 seconds. So there's more space between the presentations in C1. So you can see how an experiment like that's actually not a ridiculous experiment. I can even tell you how it would turn out. Like it's not ridiculous. And we now have, so now we're going to have 8 groups, not 4. But the logic is exactly the same. So this is just a 2 by 2 by 2. This is a 3-way ANOVA. Okay? It's a 3-way ANOVA. There. So now what happens? Now we have 3 main effects, A, B, C. So 3, what were they? Retention interval, memory test type, and presentation, right? Mass versus distributed. We have 3 two-way interactions, A, B, B, C, and AC. And we have a 3-way interaction, A, B, C. A 3-way interaction is when a 2-way interaction changes depending upon some level of the third variable. Remember, a 2-way interaction was just that the main effect changes depending upon the level of some second variable. Well, we'll just go up one level. So now a three-way interaction is when the two-way interactions change depending upon the level of some third variable. One of my favorite little questions I used to give to see if people were thinking on quizzes was, I can now tell that this is obviously not coming up on a quiz you're going to get because I wouldn't tell you a question. I would ask people to define what a 96-way interaction was. People get all freaked out. Some people get all freaked out. I don't know that. We haven't talked about that. Well, the 95-way interactions change depending upon the levels of a 96th variable. I didn't say tell you what the math is. I just said, what is it? Right? So all I'm saying, so four-way interactions, the three-way interactions change depending upon the level of some fourth variable. That's all this is. I can't think what a 96 experiment we have with a 96-way interaction, but if we had 96 variables, it's possible. Need a lot of people. But three-way interactions are common enough. Oh, I believe I have a picture of one coming up. Coming up, I do, yes. So how does this change? How did it change it? Smell burnt toast. Thank you. I'm glad in a room full of psychologists, I hope that people get that reference. Okay, our new model is x equals u plus alpha plus beta plus gamma plus alpha beta plus alpha gamma plus beta gamma plus alpha beta gamma plus epsilon. You might guess that I've said that before. That's gamma. Three-letter gamma. Okay. That's the Greek kind of g sound. We have a C there. A, B, C. They have A, B, G. What do they know? Funny looking letters. Them and their acropolises and hoplites. Okay. So what do we have? We got two-way interactions, three-way interaction. It's not that different from what we've had before. In fact, it's exactly the same. We just have more interaction terms. So we could do this with a four-way. It would be x equals mu plus alpha plus beta plus gamma plus delta plus alpha beta plus alpha gamma plus alpha delta plus beta delta plus beta gamma plus alpha gamma plus alpha plus beta delta plus beta gamma plus alpha beta gamma plus beta delta. I forget it. You know what it would do. It has 15 terms. It's got a lot of terms. But it's really just, it just gets bigger and bigger. But again, I hope you can understand that I have never once seen an article with a four-way interaction. I'm not saying they don't exist. In fact, my stats prof as an undergrad, Dr. Harshman, who taught me a course just like this at Western, he did work that actually had four-way interactions. I can't remember. It was one-handedness and sex differences and spatial ability. It was a long time ago. I have trouble thinking in four dimensions. Okay, I can imagine three dimensions and I can imagine graphs really easily. I have trouble imagining a four-dimensional graph because the fourth dimension has to be time, so the graph has to be moving, and it makes it very complicated for me. So what would a design like this, what would it look like if we had graphs of something like this? Well, it would look like this. So let's say we have our two levels of C, C1 and C2, and then we have our different levels of A, that's our lines, and then we have our B's are on the x-axis here. Oh, sorry, yes, Jen.
Correct me if I'm wrong, because
Sure.
I
will. I promise. It's my job, in fact.
Isn't this almost similar to like, because I just pulled up PSYC 2127.
Yeah.
Like between subject design, because we had to do like calculations last semester.
Yeah, we'll get there.
But is it like similar? Cause like
no, this is all between subjects.
Okay.
But you can do this all within subjects. You can do two between, two within, one between, one within, four within.
Okay.
You can do all those things. Yeah, we'll be there next week.
Okay, so I'm on the right track.
No, you are.
Okay.
That's where we're going.
Okay,
that's
because I'm like, as soon as you were doing all that, especially with the graphing, I'm like, wait, this looks familiar. And then I found my notes and I'm like, okay, so I thought I would ask. I'm like, if it is, then it makes more sense.
That's good. That was, who taught you that? Was it Taryn?
Taryn, yeah. Last course,
so I have no doubt that it's just probably better than anything I've ever done. We kind of got really lucky hiring that woman. She's awesome.
Can't wait for her to be back.
Unlike, say, Keo. I mean, so.
Well, considering the fact that
Don't,
I had to make
now remember this is being
twice.
recorded, and I'm making jokes.
Yeah, you know.
And he's my friend. There are different things here.
He's a good prof.
Yeah. He has his moments. He doesn't make fun of me, does he? He just says nice things about me in class, right? Or does he say bad things? I hope he says
No,
bad
I don't
things.
think he made fun of you at all last semester.
Really? Oh, that's too bad.
I've only had Dwayne for one class.
Okay.
so
Okay.
all
Okay. Paul makes fun of Dwayne, though, right?
these- Yes.
Good. And he makes fun of me, right?
Yeah.
Excellent. Okay, good.
Can I ask you a question?
No, I'd rather you didn't. Yeah.
The mean squared error is
Yeah.
between subjects.
Yeah.
Is that it? And mean squared treatment is within?
Okay, no,
No,
it's literally
okay.
opposite. But
Okay.
no, think about it. Mean square. So it's how much it's about individual differences. So it has to be within the group.
Okay,
Yeah.
that makes sense.
Now the thing is, the problem with those terms using with between and within groups, I don't like those terms, and I'm going to be using A's, B's, and errors all the time because, and this is because of what Jade just brought up. And you said, you know, there are times when it's all within subjects, then they're all within subjects variables. And looking at within cell or within subject variable variation doesn't make a lot of sense in that case. So I don't like that term. But yes, you're right, and you're thinking this is good. You guys are putting it together. This is what I like to see. Or, you know, I don't really see so much as smell or just vaguely sense.
Spidey senses.
Yeah.
Stat senses?
Yeah.
Statsy senses?
So I sort of think, does Paul make jokes about that? Call me blind? Because I'm really hoping that's what he does. Does he?
Yeah.
Excellent. No, it makes me happy. It doesn't bother me. I think it's funny. So I was telling, oh no, she's not in this class. Somebody I met office hours. I got a thing once on my evaluations. It said that I was unprofessional for making fun of other professors. Well, fuck you. Oh, come on. They're all my friends. These are my friends. These are my friends. You can somehow maybe guess the ones I don't like or the ones I don't make fun of. Right. It's just easy with Paul and Dwayne. And I've known them a long time.
Is it a good friendship if you aren't making fun of
I think
yourself?
that's, I think there's something to that. I think there's something to, and like we're people from the outside would think we're being very vicious to each other, but it's all comes from a place of love, right? So it's kind of cool and a good thing. So, not that I love Paul, don't say that. All right. So I think you can see this kind of, this isn't complicated, is it? I think we've seen designs like this when we read papers, yeah? Okay. So let's think about these designs, and I'm going to always sort of, when I say end up, don't worry, there's other stuff I'm going to talk about, but it won't be on the slideshow thing. So, but I'll usually end with advantages and disadvantages of the design, because every different kinds of approaches have different advantages and different disadvantages. Well, we can study interactions, and so many of our ideas in psychology and the life sciences in general, so psychology, biology, are about interactions. Just think about how many things in psychology, what are some classic things we're interested in? We're interested in sex differences. We love sex differences. They're interesting. People look for them. We don't usually find them, but they're interesting. Sex differences are interactions. Males are like this. Females are like this. Oh. So you're saying a variable is affected by your sex. Oh, that's an interaction. That's literally two interactions right there. What if I said that for a three-way, it could be your sex and your handedness, because I know that does play a role, left or right-handedness, and your, what's the third variable? We could use sex, handedness, and experience doing mental rotation tasks. Those would actually, that would interact together, three things. Here's a better one though. You have two different, maybe it's better, I'm not sure. Species, retention interval, and memory test type. That would be somebody's PhD thesis, standing right here. So yeah, I mean, all my work, not all of it, a lot of my work, and the reasons that I have those letters after my name is because I did work comparing two species on how they remember different kinds of stimuli over different periods of time. Those are three variables. I was looking for interactions. We're always looking for interactions in the life sciences. right? Our theories involve these. Like, I expected to find the interactions. It's like, juncos will be like this, and chickadees will be like this. They'll be better in this kind of memory. These guys will be better in this kind of memory. It'll decay. The decay functions will look like this and this. Those are literally me describing three-way interactions. It's all I'm doing there. Right? And as I said, sex differences are always interactions. Anything where you have differences in another variable is an interaction. We're just looking for interactions all the time. Take a look when I hope some of you come to the thesis conference. Is that what's that, the place on Great Northern there?
Water
Tower. Yeah, it's there. So I don't know why we did that. Because, anyway, it doesn't matter. But you should come. It'll be fun.
Did they announce the dates yet?
Probably. I wasn't paying attention, though.
I don't think so, because like I know, like even though the Discord's kind of died down this year, normally they kind of mention it.
It'll be at the end of March or early April, yeah. And it'll be great. And then after all the talks, we all just move right over to the bar. And you can buy me drinks. You can. I'm not saying you should. It's possible to buy me drinks. You don't have to. You don't have to if you don't want. If you don't want bonus marks. Once you've done this a few times, it's actually, and I hope that we say sex differences, and you go, oh yeah. When you've done this a couple of times, it's really not that hard. It's a matter of, because normally we aren't dealing with A's, B's, and C's, we're dealing with, species, retention interval, and memory test type. And when you look at that, you go, I expect the graphs to look like this, this, and this. Okay, so those are the upsides that I could think of. The downsides. Is it a fixed model, a mixed model, or a random model? Now, that's not a huge thing, but it still nags at the back of my mind that we're kind of maybe doing it wrong. So it does bug me. So that's one question. These things can get really big really fast. Okay? They can get very big very fast. And you might think, what's the downside of that? Well, how are you got to get subjects? You got to get research participants. And that's a battle I know our fourth year honors students go through every winter. You've probably been pestered by your profs, by your colleagues, and here's your prof again, pestering. You can sign up for those experiments that are in the LMS, please. It would really help all, and there's fellow students, and you will be asking people to do it next year. Right? Just saying. And they're fun, you get to learn a little something. Some of them are really short. 2 of my students only take about 10 minutes. The other one's only 45 minutes. Just saying.
I've done a few, they're really short.
Okay, good.
My shows is 30 because I have to do hers on Thursday.
I will say that one of mine one of my students has some Mad Men content in theirs. That's just dumb luck. Okay, let's take a look how big these things can get. All right, so let's take a look at how big this can get. So, 4-factor design would be A, B, C, D. Right? And as I said, I've never encountered one that I've read. Dr. Harshman told us in a class about some work he did that got published in a 4-way. I remember when he said it, he actually told us about it because we didn't believe such a thing existed. So it can happen. 4-way interaction. So we'll do 4 variables. So here's the model. Now it gets bigger. X equals mu plus alpha plus beta plus gamma plus delta plus alpha beta gamma beta gamma alpha delta beta delta gamma alpha beta gamma alpha delta gamma beta delta gamma alpha beta delta alpha beta gamma alpha beta delta alpha beta delta gamma plus epsilon. So you would be doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 F-tests. I'd like you to try interpreting that. Even if we knew what the variables were. 4 variables. Remember we talked about ordinal and disordinal interactions. Would you feel comfortable talking about the two-way interactions if there's a four-way? I don't know. Like, it would be hard. So these designs are great, and they're the basis basically for all the bigger, cool designs we have in, science, but they can get hard to understand. So like I said, that's 15 F tests. That's a lot of F tests. That's a lot of F in tests. I guess I think a little difficult. And you know, if we had now a fifth variable, if we had a fifth, that wouldn't be epsilon, right? Because that's error. So it would be it's zeta, I think, probably. So then we have an extra one here, and then we have all these extra interactions. It would actually be, I think it would be 29 terms now. I think so, yeah. It's insane. It's kind of ridiculous. So I don't know how to interpret things like this. Graphing them's hard. Like, I can look at a graph, this graph just back here. So if we go back, this one here, yeah. So if I look at this graph here, I can take a look at this and see pretty clearly what's going on. I can see that this group C1 behaved like this, and C2 were like this. C2 had this disordinal interaction, C1 has this ordinal interaction. I can look at that and I can make sense of it. If I had now a D panel, this would be D1, and then D2 as a whole is other ones that look different than this. It's going to get hard, man. And that's only with 2 levels of each. What if I had 5 or 6 levels? So the other thing is so A, B, C, D, so I have what? 16 cells with a 4 variable design. 16 cells. So if I need 10 people per group, now I need 160 people. Powers analysis will probably tell me I need about 15. So now it's not that. It's not 160. It's 260 and 80, 60 and 40. 240. Holy Christ. I mean, that's a lot of people. It's a lot of subjects. It's hellish. That's a nightmare. You don't want to design an experiment like this. The other reason people don't design these experiments is that they're unwieldy. Like, it's very difficult to do anything with something like this. You can't. Right? So this stuff becomes incredibly, they're useful, but they can get stupidly big. And at that point, once they're stupidly big, these advantages kind of go away, and we start worrying about the downsides here. These things get really huge, and it becomes incredibly hard to interpret them. All right, questions on this kind of design? All right, so let's stop recording, and then we can look at some other stuff.